Hi there! Welcome to the 13th episode of the Synth project, where we are going to build a synth together. It is finally time to do the final adjustments to the 3130 VCO, test it and install it in the rack, ready to be used in the synthesizer. Watch the video till the end to see some of the interesting things that can be done with this featureful device. Let's begin immediately. We start by inserting in its socket the UA741, the IC that provides the reference voltage. When you insert it, make sure that all the pins go in correctly. Since they are very thin, they can easily bend and remain disconnected from the socket. Pay also attention to the position of pin 1, which is this one on the upper left. To power up the VCO module, I'm going to use this piece of equipment that I already used to test the power rails, as you might remember. I'm inserting the connector in this socket here, and then I will connect on the board the 4 alligator clips carrying the voltages from my benchtop power supply. First the plus 12 volts carried by this red alligator, then the plus 5 volts on the green alligator, the ground on the black alligator, and finally the minus 12 volts on this orange alligator. Now I am going to connect the multimeter probes to measure the value of the reference voltage. I'm using my benchtop digital multimeter to do the measurements. The black probe goes to ground, which is available on this green connector. The red probe goes instead to pin 6 of the IC, which is the output of the voltage reference circuitry. Now I turn on the power supply, and then I start adjusting the potentiometer until I read the voltage of 2.5 volts. And yes, I would like to have a reference that is precise up to the third decimal digit. Continuing the potentiometer adjustment, and now the most difficult part, to adjust the last decimal digits to read 0. OK, done. Once you have done this adjustment, however, leave the VCO powered for another 30 minutes and check again the voltage. You need to make sure that the Zener diode is at its working temperature to minimize any possible error caused by the heat. Let's now add all the remaining ICs on the board. When you insert the ICs on their sockets, make sure you orient them correctly, otherwise the circuit will not work and you could even burn the components. Let's now insert the next IC, and then the next, and finally the last 8-pin chip, which, being down there, is a little more difficult to handle. Just be patient and there will be no problem. And now the last chip, the SSI2130, mounted on its breakout board. Even if this component is much bigger than the others, keep using the same precautions for it. And here is an aerial view of the whole inside of the module, which is now completed, at least from the hardware perspective. And now it is time to check all the functionalities of this VCO module. I have already connected all the cables from the bench power supply to the module. We have 4 cables in total, the one for the plus 12 volts, the one for the 5 volts, the one for the minus 12 volts, and the one for the ground connection. The first thing I will do is to check all the direct outputs here on the bottom row of jack sockets. For that, I will use my oscilloscope, which will connect to the jack sockets with this contraption that I made, which is essentially a coax cable with a jack at one end and bare wires at the other end, so I can connect the oscilloscope probe to the bare wires. The actual probe is connected to the central wire of the coax cable, while the ground alligator is connected to the coax shield. So let's start with the triangular wave. Here is the image on the oscilloscope, but I need to adjust the controls to be able to see the whole wave. And here it is. The oscilloscope is set to measure 1 volts per division, and so this wave is about 5 volts peak to peak, so it goes from plus 2.5 volts to minus 2.5 volts in each period. We have also a frequency of 27 Hz, about 25 Hz, which is basically the note A0, which I obtained by adjusting the transpose potentiometer. This is the minimum reasonable frequency in the audio region, although the VCO will be capable of outputting in frequencies much lower than that. Let's now move the jack to the ramp wave. This switch will allow us to invert the shape of the wave, and actually from the perspective of the pure sound, having the switches set one way or the other does not change anything really. But if we want to use the wave for some special purpose where we actually need it in one direction rather than the other, we can use this switch to change the direction of the ramp. And here is the signal on the oscilloscope, and right now it shows a descending ramp, usually called sawtooth. And if we act on the switch, we can invert the wave, and now we have an ascending ramp, usually called simply ramp. The frequency of this output is of course the same as in the triangular wave, and the amplitude is also between plus and minus 2.5 volts, as expected. Let's go now to the square wave. Well, look at the oscilloscope. It looks like the peak-to-peak voltage of this wave is too much. Different than the expected 5 volts peak-to-peak. It looks like I made a calculation mistake, or there is something wrong with the datasheet. See, if I change the oscilloscope setting to 5 volts per division, I can see the whole wave, and it looks like it has a peak-to-peak amplitude of about 13 volts, which is way higher than it is supposed to be. It seems like I have amplified the signal twice as much than it was necessary. We will need to take a look at the schematic in the datasheet to understand what is wrong and how to fix it, but for now, let's continue the testing and postpone this fix to later, along with anything else wrong that we might find. Now, let's check the sine wave. And let's put the oscilloscope back to 1 volts per division. And yes, the sine wave seems to have the correct amplitude of 5 volts peak to peak. Let's now check the pulse wave, which seems to have the right amplitude. Yeah, and let's now test the control for the duty cycle. I am now increasing it, and you see how the positive side is wider than the negative. And now in the opposite direction, thus reducing the duty cycle, which now has the positive part narrower than the negative one. And this concludes the testing of the independent outputs. Let's now take a look at the mixer output. I have inserted the jack in the mixer output, but we still don't see anything because the control voltage for the signal levels are all set to 0 volts. But now, let's increase the control voltage for the ramp signal. This should cause the level of the signal itself to increase. And in fact, the oscilloscope confirms that. And you can see that I can now control the signal level just by acting on the potentiometer that provides the control voltage to the specific channel of the mixer, which is in fact a VCA. I can also act again on the inversion switch, and you can see how the wave changes from ramp to sawtooth and vice versa. Let's now turn off this channel, and let's work on the triangular wave level, which seems to be fine. Yeah. And now to the pulse, for which I can also change the duty cycle. I will now set up my function generator to provide a signal that I can inject on the remaining 2 channels of the mixer. The generator is currently set to generate a 5 volts peak-to-peak sine wave. The frequency is 10 kHz, but let's reduce it to make a more significant value, something that is more like a real note. Here, let's leave it at 1 kHz. Now I am going to use another cable with an open end to the aux1 input. And I have also attached the open end to the output of the function generator, ground with ground and signal to the center wire. Let's now increase the control voltage and let's see what we have at the mixer output. Here, yeah, we have a nice sine wave, and we can also change the frequency of the function generator, and that is reflected at the output of the mixer. Let's check the other aux input. And yes, the sine wave is there again, and I can control it through the control voltage applied by this potentiometer. Let's now see if we can actually mix together various channels of the mixer. So we have a sine wave to the aux2 input, and then we have 3 more waves available at the last 3 channels of the mixer. Let's play a little bit with these 4 potentiometers and let's see what happens. I'm increasing first the sine wave signal, and now I'm adding on top of it the triangular wave. Hey, look at that! Since the sine wave and the triangular wave have 2 very different frequencies, we have this odd interaction. Let me change the frequency of the sine wave to approximately the same value of the triangular wave. And let's also adjust the timing of the oscilloscope so we can look better at what happens. So look now at what happens to the shape of the mixed wave. Look at all the things I can do to the output wave just by changing the input signal, both in shape and in amplitude. Okay, enough with this game. The mixer seems to work just fine, and I think we have already tested enough for now. Let's go back to the drawing board to understand what is going on with the amplitude of the square wave. Here is the part of the schematic where the output circuitry of the square wave is located, and as you can see also the output circuitry of the saw and the triangular waves. They are basically the same, and they are based on the assumption that the level of the output signal on the SSI2130 is the same for all these outputs, which, according to the datasheet of the IC, goes from 0 to Vref. Since we want a signal that goes from minus Vref to plus Vref, once the DC component is removed, we need to amplify the signal by a factor of 2. And this works well for all the waves, but not for the square wave. Well, look at the place where the square wave signal comes into the output circuit from pin 28. There are 2 resistors of 20K, one toward the ground and another one toward the plus VCC, the plus 12 volts. And those are there because the datasheet requires them, as you can see from the diagram in the document. Also, according to the specs, these resistors are there because the square wave output on pin 28 is open collector, and it is driven by an internal flip-flop. I didn't think about this before, but the two information about the amplitude of the signal and the fact that the output is open collector are not really consistent. If the output is truly open collector, the max amplitude of the signal should be plus VCC, not plus Vref. And in reality is not even that. Because I have put an amplifier with a gain of 2 and I am obtaining a wave of double the size I want, it means that the open collector configuration provides really an output of 2 times Vref. To fix this problem, I will just need to modify the value of resistor R9, making it 220K instead of 430K, and this should be enough to bring the amplitude of the square wave signal at the right value. Let me pause the video for a moment to do that. Yeah, okay, I'm back, and I have replaced the resistor. Time to check if the amplitude of the square wave is now fine. And yes, it is. Don't worry, now that the fix is tested and works, I will also update the schematic with the correct value of the resistor, and I will update the repository on eleneasy.com as well. And now that the VCO is tested and it is working fine, it is time to do the final tuning of the exponential converter, and this is the procedure that I will follow according to the guidelines of the SSI2130 specs. The paper is divided into 2 sections. The first part lists the preferred instrumentation needed for doing the calibration, and the second part is the procedure itself, as taken from the IC specs, but expanded to clarify some not-so-clear points from the datasheet. I will also use this paper as a cheat sheet where I will take notes on some of the steps of the procedure to ease the calculations. I have already prepared the setup for executing the procedure. The VCO is already powered up, and here on the oscilloscope you can see the sine wave signal that will be used for taking all the necessary measurements. Here is the VCO, and we have to connect the frequency counter to the output of the VCO, which is the same used to connect the oscilloscope. These are the alligator clips from the cable going to the frequency counter, and I am attaching them in parallel with the oscilloscope probe. And here is the current frequency emitted by the VCO. First, we need to set up the transpose control of the VCO so that we have a readout of exactly 27.5 Hz. Right now, we have a frequency of 26.97 Hz, so I will need to increase it just a little bit. We need to be as precise as possible to make these readings, so we need to move the potentiometer very slowly. Okay, now we have a frequency of 27.50 Hz, which should be good enough for our purpose. And now we need to apply a control voltage to one of the exponential inputs of the VCO, so we can change the frequency according to the procedure. To provide the control voltage, I will use this power supply. Let's turn it on. And now I am going to connect a couple of wires to it, black and red. I am now connecting the power supply output to the digital multimeter, which is more precise than the display of the power supply itself. We will use this display to make the voltage readings. Since we have to start with 1 volts, I will now reduce the voltage provided by the generator. Okay, I went too low. Let's go up a little bit. Almost there. Here, 1.00 volts, and that's what we need right now. And now we need to read the frequency as described in the procedure. Step 1 is done. Step 2 is done. Now let's connect the control voltage to the exponential input of the VCO. And the current frequency is 56.32 Hz, which I am going to write on the cheat sheet. And now we have to increase the control voltage to 5 volts. Okay, 5.00 volts, good. And now we can read the frequency, which is 968.5 Hz, and we can write it on the cheat sheet too. Now we need to calculate the log base 2 of the two frequencies we have found. For that, I will use the online log calculator that I have shown you previously in another video. So the first frequency FA is 56.31 Hz, and the log is 5.815, which I'm writing down on the cheat sheet. The second frequency FB, which is 968.5, has the log value of 9.92. Let's write down this one too. Now we need to calculate the difference, B minus A. Let's get the calculator on the PC, and so we have 9.92 minus 5.815, and this is 4.105, which we can write down as the value dy. According to the cheat sheet, the value dx, since it is the difference of the two voltages, is of course 4. We now have to calculate the value I as the difference of A minus dy in dx. So, back on the calculator, 5.815 minus 4.105 divided by 4, and the result is 4.788, which we write down here. The slope of the exponential curve that we want to have is 1 volt per octave. So now let's calculate the value of t, which is I plus 5 times the slope we are looking for. The 5 comes from the voltage of the highest frequency of the range we are working on, and since the slope must be 1, t will be equal to I plus 5, or 4.788 plus 5, which is equal to 9.788. Now, recalling that we have made the calculations using logs in base 2, to go back to the actual frequency, we have to calculate 2 to the power of t. Let's do that on the calculator. And the result is 884.059 Hz, which I just wrote down right over here. Now, the control voltage is still set to 5 volts, and at that voltage we should have a frequency of 884.059 Hz. but we have instead a different frequency, and so we need to adjust the true input R28 to adjust the output frequency to the correct value. Here is the true input R28, and so now I will use a screwdriver to adjust the true input until we get the correct frequency on the frequency counter. We need to go down with the frequency, adjusting carefully the true input. Well, this tuning costed me about 5 minutes adjusting the true input, and at the end I was able to reach a value hopefully close enough. Now we have to apply 9 volts to the exponential input and redo all the calculations to adjust the high end of the range. So setting the 9 volts on the generator, reading the frequency, which should be 6 times the one that we have from before, which is 14,144.95 Hz. But the actual frequency here on the frequency counter is above that value, and so we have to adjust the true input R48 this time to go down to the required value. So turning the screw on the true input, and it looks like the frequency is changing very slowly. I think this is the best I can achieve right now, since I have reached the end of the true input. But this just means that we have to go back and redo the whole procedure from scratch and see if we can do better with the next iteration. So let's go back to 1 volt with the generator, and let's repeat the whole procedure. The frequency is now 56.95 Hz. Let's go now to 5 volts. And the new frequency is 981.8 Hz. Calculating the logs of these two frequencies. So first log is 5.832, second log is 9.94, and the difference is 4.108. Now we calculate the new I, which is 4.805. And now we have to add 5 to this number, which makes it 9.805. And finally, we do 2 to the power of this number, which is 894.538. And so we now have to change the first true input to get this new value. Okay. Yeah, good enough. Now we increase the voltage again to 9 volts. And the new frequency is supposed to be 894.538 times 16, which is 14,312.608 Hz. And it looks like that now the actual frequency is very close to what it should be, but since I cannot lower it any further, I will leave it at that. It seems very close to what it should be, and in any case, we are not going to use audio frequencies so high, so this error should translate to a much lower error at more reasonable audio frequencies. All done then, and we are ready to install the module in the rack. To test the VCO in the rack, we will need a bunch of control voltages, but we don't have yet any other module that can provide such voltages, and so I made this contraption that I will temporarily install in the rack. There are basically 3 potentiometers that adjust the voltage that will be available at these 3 jack sockets. And these will be the voltage controls that we will use to test the VCO in its own environment, the rack of the synthesizer. This module will be powered through the power rail of the rack, and the potentiometers will allow us to adjust the voltage from 0 volt to a maximum of 10 volts. Here is how they are connected. On one side, the potentiometers are connected to ground, so when the cursor is on that side, the control voltage will be 0 volt. On the opposite side, the potentiometer is connected to the plus 12 volts through a 1K resistor. These resistors, along with the 5K resistance of the potentiometer, provide a voltage divider that reduces the voltage of the potentiometer terminal to 10 volts. This way, rotating the potentiometer all the way, we can go from the 0 volt of the ground to the 10 volts of the voltage divider. And since the cursor of the potentiometer is connected to the center connector of the jack socket, we will have on it the required range 0 to 10 volts of control voltage. This module will be put on the rack temporarily, then I will put also the VCO on the rack. This way we will be able to do some reasonable tests with real audio and see how the VCO behaves listening on the sound it generates. I'm also debating if I should make an official module like this to have the possibility of manually creating control voltages on the synthesizer. But I'm not 100% sure about the utility of such a module, so if you have insights on possible uses of such controls, please let me know in the comments, and so you can help me make the final decision. Okay, it is now time to add the VCO to the rack. However, I don't want to put the VCO as the first module in the rack. I would like to reserve that slot for another module I have in mind that will be used to handle an exponential keyboard and a tape resistor, useful to play the instrument. So I will install the VCO leaving some space for this other module, and since this other module will have the same width as the temporary module I created for testing the VCO, I will put this temporary module at the first position in the rack. Later, when the module for the keyboard and the tape recorder is ready, I will remove the temporary module and I will add in its place the keyboard module. So, let's connect the temporary module first. So, first we connect it to the power rail, and let's check if the voltages are still fine on the power modules, just to make sure there are no short circuits. Everything seems to be okay, and so I can attach the module with a couple of screws. To hold in place the module while I lock it in with the screws, I will use some masking tape to hold it in place. I will remove the masking tape once I am done. Let's go first with the screw on top. Now we can remove the tape on the top. Now let's put the screw on the bottom and remove the tape on the bottom. Good. Now let's install the VCO. First we connect it to the power rail again. We check that there are no shorts. All the voltages seem fine. So now we fix the module in place with some more masking tape. And now let's go with the screws. The one on the top center. The one on the bottom center. And I just cut myself. Oh. Well, let's remove the masking tape. And now it's time to put some band-aid to my fingertip. Okay, I'm back. And so now, since I don't want to keep poking my fingers, I will make some little holes to make the screws enter easily in the wood. Okay, now let's insert the last screws. Bottom left. Yeah, it is much easier now. Bottom right, top right, and finally the top left. And now that everything is in place, we can run some tests to see how the VCO sounds like. To amplify the sound, since I don't have a dedicated amplifier yet, I will use this electric guitar amplifier. And since the input of this amplifier is very sensitive, I will use the mixer output only for now, keeping the signal level to a minimum. So let's connect the cable to the amplifier, and the other end to the mixer output. Now let's turn on the amplifier, and now the synth. And this is the low frequency sound of the ramp, and the triangular wave. Let's add now a control voltage to the expo input, and see how the frequency changes. Let's try now with the ramp again, and definitely this is a different timbre. Let's see now if we can combine multiple control voltages on the expo inputs.
Let's try to do something like this.
And yes, it seems the mixing of the control voltages work fine. Let's now listen to the sine wave. Now the square wave, and you can note definitely the difference in timbre. Let's try now the triangular wave. I'm going to use now this control voltage to change the volume of the mixer channel, and changing also the pitch. And everything seems to work fine, but the true beauty of this VCO will be visible only once we start adding other modules to control it, for example an LFO and a VCF. So for now let's stop right here, and next time we will start adding more stuff to the synth and enrich its capabilities. Don't forget to subscribe and enable notifications to avoid missing the next episode. See you in the next video, and as usual, happy experiments!